Okay, it's I don't know. You need it. It's a pleasure to have Paul Chaikin of NYU here to give a series of lectures in the 11-year Distinguished Lecture Series. So I've known Paul for a long time, since I was a student. He was a professor at the University of Pennsylvania. And in fact, our first paper was in 1986, and our most recent paper is about to come out. So we've sort of been working together for a while. Paul did his undergraduate work at Caltech and went on to the University of Pennsylvania, did his PhD with Tony Jensen and Alan Heeger. Then went, I think, directly to UCLA. No, or did you have a postdoc? Directly to UCLA. And joined the faculty there. Moved to the University of Pennsylvania. Then moved to Princeton, where he was for about 20 years. And about 10 or so years ago, a little bit more, moved to NYU. Paul is one of the leaders, I'd even say one of the founders, but Paul wouldn't like the word, of the field of soft condensed matter physics, for which he won the 2018 Buckley Prize of the American Physical Society. Yeah. And okay. Yeah, it's probably enough, right? I could say a lot more. We know. Yeah. Okay, so. Oh yeah, I forgot to do it. I forgot which one it is now.
I can't figure out, is this because I'm supposed to hide here? Anyway, wishful thinking. So, I really liked it that I was finally invited to talk here. I mean, I've been involved with people for a long time. I shared, when I was a graduate student, I shared the office at Penn with Penn. Dov I met when I was at Penn. What I remember most about Doug is he comes into my office one day, he takes one of the world's strongest magnets that I had, holding up a poster on my filing cabinet. He said, "Oh, let me see this," takes the magnet off, puts it down on a year's worth of data on floppy disks, destroying a year's worth of data.
They improved it.
Anyway, typical W. And when I was at Princeton, Erez had the lab, who was a postdoc for Albert Liebscher at the time, had the lab next to mine. And we've been in touch sort of ever since, collaborating. And what I was supposed to talk on today was some work that Dov and I have been doing, but Dov gave a colloquium on it already, even though Yariv said that I give much better colloquium on it than Dov. But anyway, so I'm not allowed to do that, so I'm going to tell you about some other stuff which involves Dov somewhat, peripherally. So I want to talk about some work, actually two pieces of work, which started a long time ago, which supposedly had nothing to do with one another. One was on photonic crystals and hyperuniformity, which I'll get to in a second. And the other has to do with random organization. So, is there an echo from this?
It's feedback. It's only a pacemaker.
That's what that's for. So you'll know when I die. Okay, so this first, the first involves random organization. So this is sort of the simplest model for a dynamical phase transition, which involves Colloids on the shear.
Maybe otherwise.
No. There's a feedback here. Maybe it is just better. I'll turn this off. Can you hear me?
Yeah.
Okay. So, there's a model that I made up for dynamical phase transition in colloids under shear. And it's sort of the simplest dynamical model you can imagine. I really don't know how to do simulations. You put particles randomly in a box, okay? The dynamics is, if they overlap, then you give each one a random displacement. And then you keep on doing this. And the cool thing about this system is, it evolves as a function of time, as you see, until eventually it stops. So eventually you'll see it stop. I'll continue talking. That's one piece of work that I want to describe to you, because it's interesting, and it has to do with the reversibility or reversibility transition that Dave Pine, one of my colleagues, observed in this. A completely separate topic is hyperuniformity in photonic crystals. This is a hyperuniform pattern over here. You can tell it's not ordered, it's not crystalline, it's disordered, but there's some regularity to it, which I'll describe to you. The regularity has to do with the fact that the fluctuations in density are reduced, but not so much that it's a crystal, which is the most that you can do to reduce the fluctuations. A structure like this, strangely enough, even though it's disordered and doesn't have any Bragg scattering whatsoever, gives you, when you measure transmission, light transmission through this, or in this case, microwaves, because this is on a centimeter scale, if you measure the transmission, which is shown over here in this color map, okay, as a function of frequency, which is the radius here, and angle, which is the angle of the light, or the microwaves in this case, relative to this crystal, and this is 2 dimensions, what you find is there's a big gap here in the spectrum. And in this region where there's a gap, which in this case, because this system is not a crystal, which would be anisotropic, here this gap is isotropic, which means light at this frequency, if you have a source in the center of this crystal, can't get out in any direction, and it's trapped. And these two things started out as nothing to do with one another, but it turns out for this phase transition, for this dynamics over here, which has actually stopped and is giving what's called an absorbing state. An absorbing state is simply where there's no further activity in this dynamic system. As you increase the density here, you get to a point at which you can never find the absorbing state. And at that phase transition, what Dove and Daniel Hexmer, who was a student here, showed, at that point, the system is hyperuniform. Not necessarily like this, but hyperuniform. And hence the configuration of the particles that you might get at that critical point might be right to do something which you can't do in an equilibrium system. It turns out you can't get this hyperuniform structure except in a crystal, okay, from an equilibrium system, just from potentials. But for a dynamic system, you might be able to get it, and you might be able to then create a material which has this property that gives you an isotropic photonic phase. So that's what I want to describe to you. The people involved here, so there are really 3 different projects here, are Paul Steinhardt, who was Dove's advisor, and worked on the Photonics, a graduate student who is now a professor at San Francisco State, Wayne Mann, Sal Torquato, and Marion Florescu. The random organization, that has to do with photonics and hyperuniformity, the random organization started out with an experiment by Dave Pine and Jerry Golub, and followed up with Laurent Corté and John Royer. Here's Dove. And this is putting these two things together by this hyperuniformity of these absorbing phase transitions. And Daniel, I guess was interviewing here anyway, and a student at a postdoc at NYU who are working on this. Okay, so the first thing I have to do is show you this movie, which started all of this off on the dynamical phase transition. This is a movie by G.I. Taylor that is supposed to demonstrate that at low Reynolds number, very viscous fluid, Stokes flow, you have reversibility, time reversibility, in a very peculiar sense, particular sense. Okay, normally time reversibility means that if you run a movie forward in time or backward in time, the laws of physics are the same, which is true. But for low Reynolds number flow, you have something else, which is that if you reverse the stresses, which here just involves a gradient of pressure, the velocity, you change the sign, and all it does is change the sign of velocity, and the flow, the movie looks exactly the same going forward and backward. And in a sense, what it means is you're slave to the boundary condition. So if you have two concentric cylinders like this, and you move the boundary by moving one of the cylinders relative to the other, a particle or a fluid element in the fluid will track the same path independent of the speed that you go, and will only depend on the position of the boundary. And if you reverse that, you will exactly reverse the trajectory. And what I'll tell you is, if you've never seen this movie before, it is the only thing you will remember of this talk. Because it's an unbelievable movie if you've never seen it before. This is G.I. Taylor. G.I. Taylor is a fluid mechanician, who did experiments in theory. There are lots of instabilities named after him. This is a very viscous fluid. It's between two concentric cylinders. He injected ink in it, and now he's rotating the inner cylinder, and you see that it disappears. Right? And you have no doubt that if I run the movie backward, it's going to come back. And to make sure that that's not what's going on, he takes his finger off. He puts his finger on the other side, and he unwinds it, okay? And he's not necessarily going at the same speed or anything like that. He's just going to make the same number of turns. And what you see happens, amazingly, is it comes back. That's a beautiful thing.
Didn't just run the movie?
What?
Didn't just run the movie?
I said he put his finger on the other side, just to show you that it wasn't run backwards, right? So he reversed it, right? But it's amazing, right? Because it looks like I ran the movie backwards, but it isn't. Okay, now the question that occurred to Dave Pine and Jared Gala, who are two very clever experimentalists, is what happens if you put particles in there, okay? Now it turns out if you put particles in there, if you put two particles in there, the answer is known, essentially exactly. The two particles essentially approach one another. This is in a shear flow. They approach one another. Lubrication forces push them around one another, and they actually go out on the same streamlines they came in. And that's reversible. Okay? Now the question is, what if you have more than two particles? And it turns out many years ago, when I was back at Exxon, as well as being in Princeton, we did some experiments in sedimentation. And when particles sediment in a very viscous fluid undergoing Stokes flow, okay, you look at them and it just looks like they're going down. Okay? But it turns out the motion, if you do the time lapse, is chaotic. Okay? And so for more than two particles, the system is chaotic. It's not just, reversible, like I showed you before. And it turns out in the same year, in the same month, there was a theory paper. It turns out if you take two particles and you let them sediment, one of them is creating a flow field and the other one falls in that, so the two of them fall together faster than a single one would, either in this configuration or in this configuration, or in this configuration for that matter. And if you take three particles, then they'll do a dance, and then two of them will go off faster and leave one behind slower. And the one that gets left behind, if it's yellow, red, or blue over here, the one that gets left behind is exponentially sensitive to the initial conditions, so it's chaotic. So it's known that even for three particles, okay, you have chaotic flows in Stokes flow. Okay? Now, the question then is, just because it's chaotic doesn't mean it's not reversible, right? Because you're going to reverse it, and of course chaos takes some time depending on the Lyapunov experiments to develop. And so what Jerry and Dave and John Brady and Chansky was here, okay, did the simulations for this experiment. What they did is they looked at the same geometry, exactly the same geometry as G.I. Taylor's experiment, but with many particles in there. And so they're just going to take the system, concentric cylinders, and change the amplitude of the oscillation. The speed doesn't matter so much as long as it's all at low Reynolds number, at very low Reynolds number. Their Reynolds number was 10 to the minus 3 over here. And what they wanted to see is whether this was reversible or not. Okay? And so here's what their system looks like. It's low Reynolds number, it's high Peckley number, so diffusion doesn't matter so much. There are 1% tracer particles here, so all you're going to see moving here is this 1% of the particles. There are 99% of the particles, they're index matched, so you don't see them. And what you see here is when you oscillate it back and forth, you see the motion, and you see the extent of the motion, but of course you can't tell from here whether they've come back or not, because the whole thing is moving too much. So the obvious thing to do is to strobe the movie and look exactly at the same point in the cycle. And when you do that, what you find is this. This is for a strain of 1, and this is actually, this is actually now a movie because you can see the dust and stuff like that sedimenting in the background. Okay? And essentially they're not moving, so it looks like it's still reversible. But then a really strange thing happened. Instead of stopping here and publishing their results, what they did is they tried a different strain, a higher strain. And what they found there is this. This is again a strobe movie, but it's clear now that the particles haven't returned to the same position, so it is not reversible flow. And this was kind of funny, strange. And in fact, what they found is that the effective diffusion constant, there's essentially no thermal diffusion in this problem because the particles are big and the fluid is very viscous. They essentially found no diffusivity over here until this threshold, and then at the threshold you got a different diffusion characteristic along the flow direction and perpendicular. But in any event, there was a real threshold, so it sort of looked like a real transition, which wasn't known before then. This is a really striking result. And by this time, by the time this was published, Dave had moved from Santa Barbara to NYU, and he told me about this, and I thought about the experiment, and I said, well, why does that happen? How do you get a transition in there? And what they said is, oh, well, it's because of this business, part of which you had to do with a couple of years ago, which has to do with the fact that for two particles, right, it's reversible, it's known as reversible, not chaotic, and for three particle interactions, it's chaotic. And so they said the transition had to do, if you shear a little bit, you get two particle interactions, if you shear it more, you get three particle interactions, etc. I thought about it for a while, I said, that can't be right, you can't get a transition from that, because after all, the claim was this is a random suspension of particles, and if you have a random distribution of particles, sometimes you have two particles close together, sometimes it's less probable you have three particles close together, or four, or whatever. So you can't, by changing the amplitude of your strain, go from no three particle collisions to three particle collisions. You can't have a transition like that. All you could possibly have is a crossover. right? And you're not going to have a real transition. And I argued with them, and I couldn't convince them. And so I said, since I couldn't convince them, they're both pretty smart guys, I said, maybe I'm wrong, or maybe something else is going on. Okay? So I said, I said to them, I'll show you by a simulation, okay, that you'll never get this effect of two-particle collision, etc. Now, so what I did is I set up a simple simulation. It's the simulation I sort of showed you before, but here, instead of just overlap, I put in the fact that I'm going to strain the system. So I put particles in a box, I throw them down randomly. I put on a shear, a strain like that, a shear strain. I don't know how to do hydrodynamics. Hydrodynamics is really complicated. Moreover, I certainly don't know how to do what happens when two particles come close and they be contact. Okay? So I said, okay, I'll put in phantom particles here. I'll do an affine deformation. And if these particles during the strain cycle overlap, okay, I'll say they've had a collision of some sort, and they're going to move. They're not going to be reversible then. I'll bring them back to the initial positions. Okay. I don't know how they'll move from that. Okay. And therefore, I'll just put in a random displacement. Right? Because I don't really know how to do the hydrodynamics here, which is fairly complicated. And then I'll just cycle this. And what I did is I set up a simulation. And the simulation, this is again strobe, so I'm not showing you deformation. I'm just showing the position of the particles after I've strained it and let it come back, and if they've contacted or overlapped, I move them. And you see, it looks like over here this isn't affected, but it eventually gets infected by the active regions coming over. And what you can really see here is this is a higher strain than that. Here the activity continues, but here the activity is dying out. Now I'm really an experimentalist, so the first thing I did when this happened is I hit my computer like that. It had a different effect here than I expected. It's bad. Yeah. So now I gotta get it back on. There we go. Okay. So I hit it like that, and it didn't, it wasn't the computer that failed it. So I ran it again, because I figured I probably screwed up. And it did exactly the same thing, it stopped. And as soon as I saw that, I said, oh, I understand what's going on, and I also understand what they saw in their experiment. What happens is the particles collide. If the particles collide, they explore different configurations until they find a configuration where when you shear, okay, the particles don't collide. They avoid one another. So it's not this business of two-particle or three-particle collision. It's the fact that the system is organizing itself by exploring different configurations, by moving around because of the collisions itself. Okay, that sounded cool to me. Now, when you do the simulations, what you find is if you look at the activity, the number of collisions per cycle, or the number of active particles per cycle, if you are below the threshold, it decays to 0, as you saw in that simulation. And if you're above threshold, above the threshold strain, or above the threshold concentration, okay, you decrease your activity, but then you go to essentially an active steady state. Okay? And what that looks like in simulations is if you do it, there is a decay to 0 activity. This is, of course, a log plot. So when you see the 0 activity, you see this downward fall over here. There's a separatrix, okay? And above, you see that they saturate. And I'll show you this again in a while. Now, if you plot the times here, the characteristic times it takes either to find an absorbing state or to come to steady state, it diverges from both sides as you go to the separatrix. And that means that this looks like a second-order phase transition with slowing down. It's just not a thermodynamic phase transition, it's a dynamic phase transition. And the question is that really what's going on? And so we set the experiments up again, And now we did it looking for the time dependence, because the big difference between the two ideas was one was just you have enough strain in order to have 2 or 3 particle collisions, and that doesn't involve organization, whereas this involves organization, and so there's a time dependence. You change as a function of time. And so we did the experiments again, and we looked at the time dependence in experiments, and we found the time dependence. And again, what we saw in the experiments is a divergence on both sides, critical still there. So it looks like a second order phase transition. Let me see how much time do I have? Enough. And now the question came up, what causes the threshold here? Why is there actually a threshold? The first thing that comes to mind is, oh, it must just be geometry. It must just be, there's some geometry to the sweeping of the particles like this, and it's some critical geometry, some critical density because of the geometry of the area swept out. They have to collide, they have to collide, and you're never going to get the organization to work. Well, the easiest answer to that problem, because geometry is hard in anything other than one dimension, is to do the same in one dimension. So here, particles, you put down particles which occupy a certain length of the line along the line. You use the same rule that you are going to, if they overlap, move them, okay? And if they don't overlap, you don't move them, okay? And you get the same sort of phase transition in one dimension. And you can ask if this just depends on geometry, because here you put them down on line, and you ask at what density, what coverage of the line can I have it so they no longer overlap? And in one dimension is trivial, okay? The coverage is 1. Anything less than 1, I can have them not overlapping, right? There'll be a gap between them if I line them up if the coverage is less than 1. So the critical value, if it's just geometry, is 1, and the actual critical value is 0.9, which means it's not just geometry that gives this, it's actually the dynamics. And it's not yet understood what gives the critical value for any of the phase transitions that are involved in absorbing state dynamics. Almost, that's true. And the interesting thing about this, was interesting a little bit on its own, is the geometrical limit is 1 for the coverage. The actual critical value is 0.9. And of course, there are over here absorbing states that the system never finds. Okay? But if you make a finite system, it will find them. It's just that over here, the time it takes to find an absorbing state goes like a power law, and over here it goes exponentially with the size of the system. What that means, for one thing, is that if you do a Monte Carlo search for these states, you find it exponentially faster over here by doing random organization, which is what we call this process. By only moving things where there's a problem, okay, where they overlap, instead of moving everything, which is what we do in Monte Carlo, it's exponentially faster here than it would be in the Monte Carlos. Okay, now that's what I want to do on, that was one topic, completely different topic, photonics. People are interested in photonic bandgap materials. Why? Well, you can, if you have a photonic bandgap material, then what you can do is you can dig a channel in it, okay? If you put a photon in it, it can't get out. If you put a channel in it, it can't get in. So you can guide light around. So you can imagine doing photonics in the same way you do electronics, okay? It's also interesting just from problems like the lifetime of excited states and stuff like that, which become much longer if you can't read it. Okay, so these are typical structures, 1D, 2D, 3D structures. A lot of people spend a lot of time on this, working on making such materials. The basic idea that people have for band gaps, either electronic or photonic, is that if you have a periodic lattice, okay, then you will always get a gap at a Brillouin zone edge. This is a K space, and with that Brillouin zone edge gap corresponds to is degenerate states going that way and that way. You have two degenerate states. A matrix element that couples them quantum mechanically always gives you a splitting because they're degenerate, and the splitting is just the value of the matrix element that couples them. And the only things that get coupled in a periodic system are things whose Fourier transform is a reciprocal lattice vector, or 2 pi over the wavelength, so it's constructed with interference. And so you always get gaps at Brillouin zone edges, and that means you always get gaps in one dimension as long as you have a periodic system. And the same is true for Maxwell's equations for waves, if you have a periodic modulation of dielectric constant, as for electrons in periodic diffusion. Okay? So you're always going to get gaps in one dimension, and you're always going to get gaps at Brillouin zone edges. And the reason that not everything has a photonic band gap or an electronic band gap is that materials that are periodic are not isotropic. They have different directions. They're non-isotropic. And you'll get a gap anywhere along this Brillouin zone here. This is a square lattice, and the Brillouin zone is square. But the Brillouin zone edge over here happens at a different wave vector, absolute value of the wave vector, than it does along the direction perpendicular to the face. So if I go along this direction, I'll end up with a gap at a wave vector that corresponds to where the Brillouin zone is there. And here in the square lattice, this is square root 2 longer over there, so it happens at a different wave vector, which means a different frequency. So if I have a small dielectric mismatch, or small potential, I'll get a gap over here and a gap over here, and the gap over here won't overlap the gap over here. So if I put a photon in at this frequency, it won't be able to get out this way, but it will be able to get out that way. So it looks like, from this simple description, either I have to use a bigger dielectric constant like that, so the gaps will overlap, or what would be nice is to make a structure which is more isotropic, right? So you'd expect that something that's more isotropic than a square would do better. Okay, so hexagonal and two-dimensional will be much better. You might expect FCC, diamond lattice, something like that to be better in 3D. But what we had in mind is something that you see when you walk out in the hall somewhere over here, due to Dov and Paul Steinhardt, which is a quasicrystal. And a quasicrystal can have higher symmetries that are allowed for a regular crystal. And what we thought is maybe if you use a quasicrystal, you can get something that's more isotropic, and therefore get something where you need a smaller index mismatch, electronically, a smaller periodic potential, in order to open up a gap everywhere, in all directions. The only question was, when we were trying this, nobody knew whether for a quasicrystal you would get gaps or Brillouin zones, in particular Brillouin zones. Brillouin zones you get by perpendicular bisectors of the Bragg vectors, of the reciprocal lattice vectors, and for quasicrystals, the Bragg points are a dense set. Maybe 0 is a dense set. You can always get close to them. So they lie on top of one another. So we didn't know how to solve this. This is done with Paul Steinhardt, who sort of knows, maybe not as much as Dov does about Fourier transforms and quasicrystals, but anyway knows a lot. And he didn't know how to solve this problem, so we decided, there was an experimentalist, namely me, or at least my students, so we can answer this question. It's an experimentalist dream, right? It's a question you can't answer theoretically, but you can answer experimentally. So what we did is we made these quasicrystals, and you might think this is really easy, because nowadays you can do this with a 3D printer, but this was 13 years ago, and there weren't 3D printers, so we had to sort of invent our own 3D printer, which essentially meant we wrote with a UV laser on a vat of monomers and polymerized it, and then swept it clean, and then lowered it down and wrote the next layer and stuff like that. And so we made these, which at the time were the largest 3D quasicrystal models, at least anybody had ever made. Here's the 5-fold symmetry axis. pure among planes and stuff like that. The distance from there to there conflicting. You think this is right? I can't see. Okay, here you see. The ratio of these planes would cut through from here to here to from there to there is the golden mean.
Excuse me, what do you mean by more spherical?
Most what?
What do you mean by more spherical?
Higher symmetry. Higher symmetry than you can find in 3D crystal. But in particular, what I mean is I would like to make it more isotropic. What I'd like to find is a band gap, okay, or an effective Brillouin zone, which is close to spherical as I can. Okay? So for instance, a hexagonal lattice in 2D would give me something that's closer to a circular Brillouin zone than a square lattice would. This way. I want to know whether a circle fits it better. And you'll see, maybe see a little bit more as I go on. Okay, okay, so we took this and we went to the those models, and we just went down to the microwave background lab at Princeton and set up some microwave blurs like that and measured the transmission from one horn to the other through the sample. Actually, we added a couple of lenses over here as well, as a function of angle as we rotated. So all we could do in this case is measure the transmission as a function of the frequency, okay, and the angle of the sample relative to the beam. Okay, first we wanted to know what we're doing, so we also made a diamond lattice over here, the same way. A diamond lattice, how you calculate what the band structure is. Here's sort of the band structure in two different directions. And here is the transmission that we measured. This is the log of the transmission over here. And indeed, where there's a gap, you see the transmission fall by 2 or 3 orders of magnitude, suggesting that there is a gap. Okay, so now, this is what we did from calculations for what the transmission would look like, okay, for the diamond lattice. And you can see clearly here, the blue here is low transmission, and there's low transmission on the Brillouin zone, which in this case is just cubic, or in this projection, just square. What we measured for the diamond lattice is shown over here in the along the fourfold direction and along the twofold direction. Okay? Here's what we got for the quasicrystal. Now, it hadn't been known before this that there was anything like a Brillouin zone for a quasicrystal. But you can see here that just looking at the transmission, and again, what I'm plotting here is the transmission from this polar map in terms of the length of the arm here. The radius is the frequency, and the angle is just the angle relative to the beam. And so you can see here is the Brillouin zone, and over here it looks like you're seeing a Brillouin zone. You're seeing a whole bunch of Brillouin zones here. But a dominant one right over there. And the question as to whether you can get a full photonic band gap is whether the band gap in all directions fits, whether a sphere, let's say in all directions, a spherical shell, okay, fits inside that gap. And here you can see that for the diamond lattice, and this is sort of what I meant by more spherical. Here you can see just from the symmetry here, yeah, you're touching over there, you're in over here, but you're not nowhere near the gap in that direction or over here. And this way you're far from, of course, that. But here, for the quasicrystal, this is along the twofold axis, and this is along the fivefold axis, which in reciprocal space is tenfold. Okay? This is a decagon here. Here it essentially fits almost all the way in, but you're missing points, some points over here, and over there, and over there. Okay, so that's what I meant fits better. So it actually looked at this time like quasicrystals probably the best candidate for a photonic bandgap material. Hyperuniform. So now I'm going to go on to hyperuniformity, which is kind of cool. The only thing I'm really known for in the soft matter or the physics community is an experiment I did 15 years ago or so with Sal Torquato. And what we did is we showed that M&Ms pack denser than spheres do. Okay? Ellipsoids, I should have said it. Ellipsoids pack better than spheres do. Right? And we did the experiments with M&Ms. And this is a barrel of M&Ms, and that's Sal, and that's me, and that's the experiment. Okay, anyway, Sal is known for philosophy. One of the things that Sal is known for is he studies geometry of packings. M&Ms are part of it. But he came up with an idea of looking at the uniformity of packings. What he said is, suppose what we do is we have a random point distribution. Okay? And what I'm going to do is I'm going to draw a circle or a volume of some radius here, some radius over here, and I'm going to find the average number of particles in there. And the average number of particles is just going to be proportional to the volume times the density. So n is just proportional to d. Now the question is, if it's a random packing, okay, and now, or a random point distribution, and I take that volume and I move it around, I want to know what the variance is in the number that I'm going to find. Okay? And it turns out the variance, if it's a random distribution here, plus one pattern, then the variance just goes like the number, which also goes like v, which depending on the dimension goes like r to the d. It generalizes. So this is sort of what you get for a random distribution. So random you usually think of as uniform. That's a random distribution. You can make something that's worse than that by making a fractal or something like that. Right? Make it so the variation is even greater than this random, this uniform. Now, how good can you get? How much can you make it uniform so the variance is as small as possible when you move the circle around? And what you would guess at first is if you took a crystal, something that was periodic in space, okay, when you move it around, you know, inside it's exactly the same distribution, so you think it might be, the variance might be nothing, but it's not true, because if you look at the edge over here, as you move this guy around, sometimes that point is inside and sometimes it's outside. And therefore the variance is going to go like, is like the area, maybe times some thickness, like the distance between the lattice points over here, like the lattice constant. So it would be something like the area, okay, or the dimension less than whatever the volume of whatever dimensional space you're in, okay, times essentially the lattice constant times the density. Okay? So at best, the best you can do is something like a variance that goes like r to the d minus 1. Okay? And he called these hyperuniform because they're more uniform than random, which is considered uniform. Okay? More generally, you can get something dr to the d minus alpha, where alpha is between 0 and 1. And what this hyperuniformity implies as well is that the structure factor goes to 0. It's like it's an incompressible system. S of q goes to 0 as q goes to 0, which is what's shown. And this was work that was done by Sal, and then the interesting part. Sal, okay, so I was working with Steinhardt on Photonics, and I was working on Sal unpacking M&Ms, and we got all together at one point, and Sal started talking with Paul, and they came up with this weird, or really Sal came up with this weird idea. He said, well, you know, photonic crystals are hyperuniform, and they have photonic bandgaps. Quasi-crystals also are hyperuniform, just like crystals are. Okay? same R to the D minus 1. Right? He said, so we know that two things, one's a crystal, one's a quasi-crystal, both are hyperuniform, both can have photonic band gaps. Okay? Maybe what's important is not the Bragg scattering, is not the crystallinity or quasi. Maybe it's the hyperuniformity, he says. So he says maybe what we should do is try and make something, okay, which is not crystalline, which has no Bragg scattering, which is disordered but hyperuniform. And he had written a code to make structures like this, which have the same hyperuniformity as a crystal does. That is, delta n squared, the variance, goes like R to the D minus 1, but there's no periodicity. And you can make them a point pattern like that, or you can make a cellular pattern like that, either by a one-odd tessellation of this, or by another tessellation that South came up with. But these guys clearly are not a Poisson distribution, but they're clearly not crystalline either. And the question was, would you get a photonic band gap from that? So we went back, and by now we could 3D print these guys, and we 3D printed the two-dimensional square lattice and the hex lattice, and this guy, which sort of looks like a foam pattern, is what you get from the hyperuniform disorderly theory. So what you do now is you measure again, just by doing transmission of microwaves through these guys, you measure where the gaps are, which are in blue over here. The square lattice has Bragg scattering. That's the Fourier transform. Hex lattice has a Mogen-David for a blue-line zone over here, and it's got Bragg scattering. Penrose tiles have Bragg scattering and a nice band gap. This is hyperuniform disorder. No Bragg scattering whatsoever, essentially an isotropic band gap, which is at least as big as any of these guys. So this means that, in fact, periodicity is not what's responsible for band gaps and stuff. In some cases it is, but you don't need periodicity to get a band gap. Okay? I should also mention, this is a band gap. It means there are no states in the gap. It's not a localization problem. It turns out near the edges of this band gap, over there and over there, there's localization, but there are in fact no states inside here, which now we know not from the experiment, but from calculation. Okay. We decided to play with this structure. So we sort of made a Lego set out of it. We have rods and plates and a pattern where you can insert them, and now you can take them out as you want. And this was on my original slide, the pattern that I showed you, with walls and everything. This guy, it turns out, you do with walls and point and rods, because it turns out this has a photonic band gap which overlaps for both polarizations in plane electric field and perpendicular to the plane magnetic field. So light doesn't get out in either direction. And what you can do is you can put a channel through it. The interesting thing is, for a usual photonic crystal, you can only put channels through it in symmetry directions. But here you can put any channel through it, okay, and you can get in the gap transmission through this channel. So you can direct light, or in this case, microwaves any way you want. You can also put things in here which give you splitters, frequency splitters, which give you putting the green host back in over here, you get a very narrow transmission region, which is selective depending on where you put the host back in. So you can start to imagine doing either microwave, which is what we were doing before, or IR. This is actually patterned in silicon. Waveguides, directed waveguides. These are completely different things so far. until dove over here, and probably began to fix it even more. Yeah, probably to get fixed it even more. Said, it turns out at this critical point over here, okay, the system's hyperuniform. And what they did is they looked at the variance, okay, for critical absorbing states. The model I just showed you, this continuum model, which I came up with, we call random randomization. When I did that, I didn't even know there were any other absorbing state models around, but it turns out there are many. Okay? There's a Manna model, there's sort of lattice gas model, stuff like that. And what they showed is that as you approach the critical state, this is essentially what the variance is as a function of the length of the system. As you approach it, you come down from something that is 2 minus 4.5, 2.45. That corresponds to alpha 4.5 over here in uniformity. So the variance goes like this is 2D. Anyway, so you go to something that's hyperuniform, and that's in 2 different models. This, by the way, is really shocking because these are dynamic phase transitions, and in conventional thermodynamic phase transitions, you get exactly the opposite thing. At the critical value, you essentially get a fractal distribution here, okay, a self-similar distribution of your fluctuations, if you like. Okay? So you have divergences. You have it very, very inhomogeneous, non-uniform. And here in the dynamical phase transition, what they found is at criticality is hyperuniform. Okay. So the question is, can we use this to make photonic bandgap materials? So what my student Sam Wilkins set up was a system where now you could do on a colloidal scale, because you want a colloidal scale for the wavelength of light. You want to see whether you can make a system hyperuniform here. And we don't really know the answer yet, but the experiment is done with a cone and plate over here. So as you rotate the cone like that, you're shearing the sample. There's a cover slip over here. This is jittering back and forth because he took it with his camera. He took it with his cell phone camera. Okay. But this plate is held in place, and you're rotating the cylinder underneath. So you're shearing, and you shear back and forth like that. And you look up at this from underneath the microscope, actually from the focal microscope, so you can get a 3D image. What it looks like when you're shearing it is like this. There is dyed fluid, and these are the colloidal particles, so you can see all of them. It's actually kind of cool. The question is, how do you know when you're critical? It turns out you can use the system to find its critical value on its own. What you do is you start up above this transition, above this critical value. You start at a strain which is high, which will give you something as a function of number of cycles. This is the activity which goes out over here. So you start at a high strain, then you lower the strain, you follow this curve, you lower the strain, you follow this curve, you do 400 cycles there, 400 cycles there, 400 cycles there. Eventually, you cross the criticality boundary, and here you get absorbing states, and then you just die. And anything lower than this also dies. And what it looks like is this is an image that's strobed. So after every 400 cycles at a particular strain, you take a picture. And now we're going to lower the strain through critical. And you can see everything's moving around like crazy, and you cross critical, funk, it just stops. So you've reached the absorbing state. It's actually, we're still going 400 cycles here, 400 cycles, but it comes exactly back. And the initial thing showed that indeed, whereas delta n squared is a function of distance leveled out over here, which should be if it's random, it's went toward what Dove predicted, a very small region. Here, it looks a little better and gives a value that's more, in this case, more characteristic of 3D. But we really don't know yet. These experiments are just starting. So it may be that we'll be able to use it. You can ask, well, what is diffusion or what is kicking the system due to this? And it turns out, I guess last year, when we did this together, we showed that in fact, not only does hyperuniformity survive noise, it loves it. What happens is they found the critical exponent initially at 0.45, and now what we find is if you do, you're at the critical value, you periodically strain the system, okay, you go to 0.45. If after you get to the critical value and you're in the absorbing state, you kick the system, or you add a little bit of diffusion, it actually goes to maximum hyperuniformity, which is an alpha of 1. Okay. Which is promising. And this shows that it works for all the different models in the world. So I'm finished, I guess. I used up my time. Here's what I will leave you with. First, you can self-organize systems into hyperuniform absorbance states. That seems to be true. What's also true, which is that disordered photonic bandgap systems exist. It turns out now it's known, okay, that hyperuniformity isn't necessary. It seems to help forgetting photonic bandgaps. But you certainly don't need a crystalline system in order to have photonic bandgaps. And you can make hyperuniform materials with these absorbing state models in real physical systems. In general, we've learned from these studies already. You can organize materials. You can make new types of materials dynamically that you can't make thermodynamically. And that's interesting. You can make hyperuniform systems and probably lots of other systems using dynamics that you can't make from thermodynamics. You can't make a hyperuniform system from thermodynamics. And the other thing that's really strange, which I'd really like to know the answer to, is once you get rid of the fact, once you show in any case from hyperuniform disordered materials or anything else you want, that you don't need periodicity to get a photonic bandgap, the question is, what do you need? It opens up a big gap in sort of a basic understanding of what gives you gaps in materials, either electronically or photonically. And that's a question that still is a basic question you need to answer. And I think I'm done, so thank you.
I just want to remind everybody that there are 2 other lectures in the series, and you can find details on the physics website and on the monitor in the lobby. And now, if there are any questions, go ahead. Sorry.
So, how you generate the hyperuniform just theoretically?
How do you do theoretically?
Yeah. You want to organize some hyperuniform.
So you want to know?
It's a grid is not.
So
Yeah, this one.
so how do you generate that?
Yeah.
So what Sal did in doing this is he says, I want to get a hyperuniform structure. Okay, a hyperuniform structure, as I mentioned somewhere here, okay, corresponds to one also. The SFP goes to 0. You can go to 0 in many different ways. You can decide how you want it to go to 0. It turns out if the hyperuniformity is alpha over here, then S of Q goes like Q to the alpha. Okay? So you decide what you want. Okay? Then what you do is you find a potential in Q space, okay, that will give that to you. You Fourier transform it back to real space, and you do Monte Carlo on that to find the ground state in that potential. It's actually fairly clever what he did. And he sort of invented it.
And what is the power spectrum there of this distribution if you apply of the distances between the
Well, I mean, it's made to give you, it does give you S of Q going to, as Q to the alpha, right? What it does higher up is not completely obvious, but because of the way you're doing it, you're working with a real distribution of particles, and so it has all of the right laws. You know, you have a positive definite G of R and S of Q, right, and things like that. But the structures are kind of funny aside from this.
some kind of long-range order, not being just random and not being symmetric, but some kind of long-range correlations.
Yeah. So, but you can make it using this. You can make it so that this is not uniform. You can make it. In fact, when you change things, you can get this anywhere from random to crystalline. Okay? And what he tends to do, the best photonic band gaps he gets, where S of Q is 0 for a finite range of Q. But even it's a clever way of doing it, of finding essentially the cell works a lot with inverse problems. There's an inverse way of finding a particle distribution that will give you a certain S of Q. Awesome.
So question one, you said there's a proof that the band gap exists and there's no states in the band gap, or is it just numerics? Because I would think perhaps you could do it periodically, starting with crystals with large band gap and just doing perturbation on making them not oriented relative to one another, but not closing the gap. Is that possible to prove?
I mean, I think when you do that, you tend to always add states inside the gap, which come from the fact that you just want to take two crystallites and rotate them, or several crystallites and rotate them. I think what you get from the interface is states in the gap. But I mean, you certainly, yeah.
So that it doesn't exist
if you perturb the positions of atoms, you tend to get states inside the gaps. So I don't think there's a simple way of going from the periodic case to this case.
I think. So you have, I assume you can also speak of photonic systems.
Sure. Photonic systems will also work. It doesn't help in terms of the fundamental thing that bothers me is once you lose Bragg scattering as being your source for having a gap, it's hard to imagine. I mean, there is a simple explanation of a way to get a gap, which is easy, which isn't clear, that isn't obvious that it's wrong here, which is you can ask, suppose I start with a gap. So I start with hydrogen atoms, you know, and I have 1s and 2s, and it's a big difference between them. And now I start bringing them together so I can hop from one to the other. Okay? And you can say, well, I will destroy that gap when the hopping interval gets big enough, right? And you say, okay, therefore I can make a disordered system by making the hopping integral from one atom to one atom to the other small enough so it doesn't wipe out the gap. But there I'm starting with a gap. It's much harder to understand how you start with something that's purely waves, like light, okay, and you end up with a gap, other than from interferences, constructive interferences.
So you mentioned a couple of times that in equilibrium you don't get this hyperuniformity other than like a lattice. But I mean, is that, if you had a crazy enough pairwise potential and 3 particle potentials and things like that, and is it clear that you couldn't?
I think it's true. Nobody's found that yet. What is true, however, is if you take a one-component plasma, okay, thermodynamically the one-component plasma is hyperuniform at any temperature. But it's a little bit cheating because a one-component plasma means I have a uniform background, a uniform positive background, and because charge neutrality holds, right, just depending on your length scale, you're essentially just matching the charges you've got to the already completely uniform background. So it's sort of cheating that way, right? And indeed, you can get thermodynamic systems which couple to something which is uniform on its own, which become hyperuniform. But without that, I don't think people found a way of doing it.
But okay, no, I misunderstood that.
I mean,
there was a theorem or something.
No, you can't do it with Schroeder directly.
I mean, that's established that you cannot do it.
You can show you.
Disorder.
Could you combine 2 hyperuniform structures, let's say different scales, and still get a hyperuniform structure?
I mean, so hyperuniformity is a property in the long wavelength, in the large distance length. Right? So if you took two systems which were hyperuniform and you add them together, they'd be hyperuniform.
So you can get different band structures by combining such systems.
What's that?
You could in principle get different band structures, band gaps, by combining different hyperuniform systems together.
Yeah, you could. But if the disorder is not, it's not clear why either of them. But what do you have in mind?
I'm imagining having something like you have on the screen right now, only on 2 different scales,
Yes.
which will still which will have this effect only on different wavelengths, extremely different wavelengths.
I have to think about it. My impression would be band gaps don't add. If there's states in one system, I don't know, but my guess is that to lowest order, in most cases, unless you compare the system especially, when you overlap them, you get rid of both band gaps rather than have band gaps rather than some of the band gaps. Because there's going to be interference in the 2 systems scales. And again, it was thought, especially by Sal, that hyperuniformity is necessary in a disordered system to get band gaps. But in the past 2 years, let's say, people have found other systems which clearly are not hyperuniform, which have similar band gaps, maybe not as big, but certainly you can get a band gap without hyperuniform. And it's not clear what's responsible for the gaps. People sort of have rules of thumb, and the rules of thumb are essentially, what you like to do is you like to have resonances inside your structures, which means that in this system, you're going to get some resonances inside these posts, and now somehow getting those resonances to match with the distances here supposedly helps, but it's not so clear. It's a little bit like what I said before. It's a little bit like setting up gaps and then making sure that you don't destroy the gaps by coupling between the systems. But none of that is really clear. It really needs an explanation.
Any further questions? If not, let's thank Paul again.